3, and 4. So, yeah. So, first, level 3. Okay. So Jackson starts at 1 on the number line. And so at each step, the chance that he remains in place is 85%. And the chance that he moves 1 step forward is 15%. And you can see that 85% and 50% sum up to 100%, so there's no other move that Jackson will make. And so we let D of n be his position after n steps, and let E of n be the expected value of 1 over D of n. And so we want to find the smallest n such that 1 over E of n is greater than 2017. Okay, so first, in order to simplify the calculations, we can just let P equal 85%. Well, this is not to simplify the calculations, but just to make it more convenient to write stuff. And so then E of n is the expected value of 1 over D of n. So E of n is the sum from k equals 0 to n of 1 over, and so here we're going in reverse order because that makes it a bit more convenient. And so we're gonna end up using n minus k plus 1. And the plus 1 here just comes from the fact that his starting position is 1 in the first place. And so next, in order to reach his current position, then his current position would be n minus k. And so in order to reach there, he needs to have 1 minus p he needs to have n minus k steps forward. And so this probability is 1 minus p to the power of n minus k. Well, sorry, his current position is n minus k plus 1. And that's the number. And so he needs to make n minus k steps forward. And so the other k steps from these n steps are all p, where p is just he stays in place. And since there are k, we now have p to the power of k. Sorry, we now end up multiplying the probability by p to the power of k. And so finally, the number of ways to order this stepping forward and staying in place, there are a total of n steps, n different times where he chooses to move or not. And in there's a total of k where he stays and n minus k where he doesn't stay and where he moves forward, so it's n choose k. And so we have that E of n is equal to this sum. And so next up, we can use the fact that n choose k is equal to n minus k plus 1 over n plus 1 times n plus 1 choose k. And so that gives that this is equal to the sum from k equals 0 to the power of n of p to the k times 1 minus p to the power of n minus k plus 1 times n minus 1 choose k divided by n plus 1 times an extra factor of 1 minus t. And so here we can see that it still remains the same because there's a plus 1 here and an extra factor down here. And so next, we can add an additional case where k equals n plus 1. We can add it in here and then subtract it out here. And so the result would be that the sum from n equals 0 to k plus 1 now is equal to p of k and 1 minus p to the power of n minus k plus 1 times n plus 1 choose k divided by 1 minus p times n plus 1. And now this is k equals 0 and to n plus 1. And so when k equals n plus 1, we can see that the end result is p to the power of n plus 1 in the numerator, and the denominator is the same because it does not depend on k at all. And that's because this simplifies to 1, and this also simplifies to 1. And k equals n plus 1. So it equals this sum. And so finally, we can see that this sum is a binomial expansion of just p plus 1 minus p to the power of n plus 1 in the numerator, not the denominator. And so this is equal to just 1 over 1 minus p times n plus 1 minus p to the power of n plus 1 over 1 minus p times n plus 1. And so these numerators are the same. So this is obviously just 1 minus p to the power of n plus 1 over 1 minus p times n plus 1. And so remember, this is equal to e of n. And so what that means now is that we have now found a closed form expression for e of n. So now we can substitute p equals 17 over 20 back in. And so when we do that and multiply, when we clear the denominators by 20 to the power of n plus 1, numerator and denominators, the resulting fraction is 20 to the power of n plus 1 minus 17 to the power of n plus 1 divided by 3 times n plus 1 times 20 to the power of n. And so 17 to the power of n plus 1 is a lot smaller than 20 to the power of n plus 1 for even just relatively large values of n. And so that means that we can just approximate this as 20 to the power of n plus 1 over 3 times n plus 1 times 20 to the power of n. And this just simplifies to 20 over 3 times n plus 1. Okay. So now we want to find the smallest n such that the reciprocal of e of n is at least greater than 2017. So we want to find e of n, the smallest value of n, such that e of n is less than 2017, because then this goes both ways. And yeah. And so we can see that e of n is basically just 20 over 3 times n plus 1. And so we want to find what this is less than 2017. And so we cross multiply, and since n is guaranteed to be positive, since we already know that he can't take a negative number of steps, so that means that we can just so that means that the sign does not flip when we cross multiply. So 3 times n plus 1 is greater than 20 times 2017. And so if we solve for n, we see that n is greater than 13,445.6 so on. And so that means that the minimal value of n is 13,446. And the reason for this is because it's impossible for him to take a fractional number of steps. It's only possible to take an integer number. And so the answer is 13,446. And so does anyone have any questions? Okay, well, if not, let's move on to the level 4 question. And so show that for any positive integer k squared factorial times the product from j equals 0 to the power of k minus 1 times j factorial over j plus k factorial is an integer. And so the way we can do this one is just by induction. And so, first of all, the base case, so we can let this just be equal to some f of k, some function f of k. And so we can see that the base case is f of 1. And if we do this, this is just equal to 1. So there's not much here. And so also, in order for the induction to succeed, we'll eventually need the fact that f of 2 is also an integer. And so if we try it out, we can see that f of 2 is just equal to 2. Excuse me for a second. Okay, sorry about that. So next up, we can assume that f of k is an integer. Then we can find f of k plus 1 divided by f of k. And so when we substitute k plus 1 into k, we find that this is just k squared, k plus 1 squared factorial times the product from j equals 0 to the power of k of j factorial over j plus k plus 1 factorial. And this is divided by k squared factorial times the sum from j equals 0 to the power of k minus 1 of j factorial divided by j plus k factorial. And so we can see here that a bunch of factors cancel out in the factorials, so this is equal to so we can see that a bunch of factors cancel out between these two factorials. So this is equal to k squared plus 1 times k squared plus 2 all the way to k squared plus 2k plus 1. And now we divide, and so next up we have these two. And so between these two, we can see that basically all the numerators get canceled out except for a final k factorial in the numerator. And so in the denominators, we can find that something similar happens. And so we can eventually see that what remains from when these two products cancel each other out is simply just 2 times 2k plus 1. And so now we can see that that means just that this fraction is equal to this. And so First of all, we can take a look at 2k plus 1. And so there are a total of 2k plus 1 factors in the numerator. So we are guaranteed that 2k plus 1 divides some factor of the numerator. And also, 2k plus 1 is an odd number, clearly, because it's one more than a multiple of 2. And so that means that as long as the numerator has more than a single number, then obviously the product is even. And so we can also cancel out a factor of 2. And so that means that this is equal to an integer. And so now this means that f of k plus 1 equals a times f of k for some integer a. And so thus we have that f of k is always an integer by our induction. And so that means, and so since this was equal to f of k, that means that this is always an integer for any positive integer. And so does anyone have any questions about this problem? All right, so if not, then thank you for coming. And so next Friday, our guest speaker will be Neil Yang. And Catherine Lee will continue going over her bi-weekly programming challenge question, and Zachary Chung will continue going over the weekly physics challenge question. And so thank you for coming and have a nice weekend. Bye-bye.